Hi, and welcome to the video on solutions to stoichiometry. This video is a continuation of your notes from last class. So I ask you to pause the video now and take out those notes. Alright, so as I said in the last class, solutions to stoichiometry is just like regular stoichiometry, but now with molarity. And these are the two equations that you need to know, the molarity equation and the equation that relates moles to the molar mass, which is moles is equal to mass over molar mass. You may need to use one or both of these equations during a solution stoichiometry problem. So before we begin, I just want to recap what stoichiometry is. In a stoichiometry problem, you're given the amount of something, and you're going to use your mole ratios to define the amount of something else. Now, the amount that you can be given could be in moles, mass, number of particles, volume, concentration, etc. And the mole ratios, you'll find those through chemical formulas or balanced equations, depending on the problem. So I just want to quickly show you what I mean by mole ratios. In a chemical formula, something like for potassium nitrate, you'll notice that if you have that in a potassium nitrate compound, you have one nitrogen and three oxygen atoms. So it's a 1 to 3 ratio. And we can scale that up from number of atoms to number of moles. So again, it'll be a 1 to 3 ratio of nitrogen to oxygen. Similarly, if you are looking at the entire compound and how many atoms are in that compound, for one potassium nitrate compound, there's one nitrogen atom. And again, you can scale it up for 1 mole of potassium nitrate, there will be 1 mole of nitrogen atoms. Now, in the case where you're given a balanced equation, the mole ratios come from the coefficients, and we've seen those before. So, for example, the ratio of potassium hydroxide to lead 2 nitrate in this equation is given as such. It's a 2 to 1 ratio, and again, we can get those from the coefficients. So the key idea with stoichiometry, if your starting amount is not in moles, you must convert it to moles. That will be the first step that you normally do. And then once it's in moles, you can use mole ratios to convert from moles of your starting to moles of your ending. Again, your mole ratios are going to come from your balanced equation or from the chemical formula. Once you have your moles of ending, you now need to make sure that you're reporting it in the correct units. So if you're not actually report the amount of your ending into moles, you have to convert it to the desired units, and that's typically the last step. So for the first and last step, you're typically using one of those equations that were shown in the beginning, the molarity equation, and the moles equal to mass over molar mass. All right, so we looked at this example in the last class. How many liters of 0.25 molar KOH solution are needed to neutralize 100 milliliters of a 0.15 molar sulfuric acid or H2SO4 solution? And we know we're looking for KOH, so that's our ending, and we're given this as our starting. So our first step is to write a balanced equation so we can get the mole ratios, and here's the balanced equation. And then the next thing that we did was we converted the amounts that we were starting with, which is the H2SO4, into moles. And we needed to pick the equation that would work. So since we're given our amount of starting in volume and concentration, which is in molarity, we used the molarity is equal to moles of solute over liter solution. We chose this equation because that was the equation that related those units. And we plugged in our numbers after we converted the milliliters into liters, since that's the unit we need to use for this equation. And we plugged stuff in and we solved using algebra. Now once we had our H2SO4 in moles, we're going to convert the moles of our starting to the moles of the ending using the molar ratios, and we got that from the balanced equation. So it was 2 to 1 ratio here, and we just plug that into our conversion factor. Notice that H2SO4 is in the bottom because we want to cancel those out, and we want to keep KOH. So we just use our dimensional analysis trick here to calculate the moles of KOH. So now we have moles of ending, moles of KOH, but they want us to report our answer in liters, and so we need to do one more conversion, and that is to convert moles of ending to amount of the desired units. And in this case, it's liters, so we need to pick the equation that will do that, an equation that relates moles to liters. And the equation, again, that we are using here is molarities equal moles of solute of liters solution. We plugged everything in, and we got our volume. So these are notes that you should have in your notebook. And just to recap these key steps, we write our balanced equation. We converted the amount we're starting with into moles using the equation, one of the equations to know. And so, again, you should know these equations. Once we have the moles of starting, we converted the moles of starting to the moles of ending using mole ratios, and we got that from the balanced equation. And then finally, we converted moles of ending to the desired amount, again, using these equations that we should know. So in a moment, you're going to follow these steps to solve some problems that were from the textbook, and there are two of them. So here are the questions. I'm going to pause the video now to solve these problems on a separate piece of paper. Any question that you are completely stuck on and you do not know how to do, even after referring back to your notes, just circle it and move on. And at the end of the video, I'll reveal the answers. You will check your answers and correct any mistakes. All right, here are the answers to those questions. Take a moment to check your answers and correct any mistakes. All right, so now this was the last problem that we ended class. We didn't get a chance to do this, so we're going to do it now. Take a moment to read this question. Okay, so they're asking us to find the number of grams of lead chloride that can be formed when we mix 100 milliliters of this 1.5 molar lead nitrate solution, lead 2 nitrate solution, and this 3.0 molar potassium chloride solution. The other thing they want us to know is what is the concentration of potassium ion in the solution after the reaction. Remember, these brackets stand for concentration of, and then that's the potassium ion. So there's two things we're doing here. Let's start with the first one. So step one is the same as before. We're writing a balanced equation. I know from this information that these two are my reactants since they're being mixed together, and lead chloride is a product since it's being formed. But this is a double replacement reaction, so the products, they're going to be more than one product here. So what I want you to do is I want you to pause the video, predict the other product, and then balance the equation. When you press play, I'll reveal the answer. Okay, so you should know that the other product here is going to be potassium nitrate. I forgot to include the phase here, aqueous, so make sure you include that on your own notes. And then to balance this off, we have 2 chlorines on this side and 1 on that side, so I'm going to put a 2 in front of the potassium chloride. And then I'm going to put a 2 in front of the potassium nitrate to balance the potassiums. Alright, so step 1 is done. We wrote our balanced equation. And now, for this problem, it's a little bit trickier because it's a limiting reactant problem. But the steps are going to be the same, except for we're going to have to do them twice. So for a limiting reactant problem, we ask ourselves certain questions to help us figure out which reactant is going to run out first, and then the one that runs out first, or is our limiting reactant, we'll use that to find our product. And the way that I'm going to do it is I'm going to use a method where I'm figuring out the amount of product I can make from each of these reactants. So the first question I ask myself is how many grams of lead chloride, my product, can I make from 100 milliliters of a 1.5 molar lead 2 nitrate solution? And so I'm going to use the same steps that we've done before. Step 2, first converting the amount of starting into moles. And because I'm given the amount in molarity and volume, I'm using this molarity equation. So I just go ahead and plug that in here. I want you to copy this information down, and then I want you to solve for the molarity. or for the moles, sorry, of lead 2 nitrate. Okay, so you should get 0.15 mole lead 2 nitrate. And that's the first step. Now what I'm going to do is the next step, which is to convert from the moles of starting to moles of ending. And I'm going to use my mole ratios from the balance equation. So I start off with 0.15 moles of lead 2 nitrate, and I want to get to moles of lead 2 chloride. In the balanced equation, there's a 1 and a 1 in front of both of these, so I just put my 1 and 1 here. And then that gives me 0.15 moles of lead 2 chloride. All right, now that I have the moles of my ending amount, I need it to be in grams because I'm looking for the theoretical yield, so I need to get that into grams. So I'm going to convert my moles of ending into the desired amount. And in this case, I'm going to use the relationship moles is equal to mass over molar mass. So you can either plug it into that equation, or here I'm just using dimensional analysis, which we typically do. So 0.15 moles of lead 2 chloride, and I'm going to multiply it by the molar mass over 1 mole, and then this gives me the grams of lead chloride. Okay, so that was just the first part of finding the limiting reactant. I still haven't figured out what my limiting reactant is. What I need to do now is I need to take the other reactant, which is the potassium chloride, and figure out how much of the product lead chloride can I make from it. So take a moment to write this information down. Okay, so now that you've written this information down, what I want you to do now is you're going to follow the same steps that was done before for figuring out how much lead chloride can be made from the lead nitrate. Using this information now, how much lead chloride can be made from the potassium chloride. So those steps 2 through 4, you're going to follow those. And then after you press pause and then play, when you press play again, you'll see the answers for each step. Okay, so for step 2, you should have the moles of KCl to be 0.30 moles. Step 3, you should have the moles of lead chloride to be 0.15 moles, and then the mass, again, is 41.71 grams. So there's no limiting reactant here, and that's because typically to find a limiting reactant, we compare the amount of lead chloride or product we can make from both, and the one that gives us the least tells us our limiting. That means that that's the one that ran out first, and so our theoretical yield would be the one that's the smallest mass number. Here they're the same, so there's no limiting reactant, and then our theoretical yield will be the 41.71 grams. Okay, that was the first part. The second part is what is the concentration of potassium left in solution. Now for that, what we need to know is that concentration is measured in molarity, and the equation for molarity is moles of solute over liters of solution. So what do I need to know for that? I need to know the moles of K plus because that is my solute. And I need to know the volume of the solution. So to understand that, we kind of have to visualize what's happening here. We're taking 100 milliliters each of a potassium chloride and a lead 2 nitrate solution. And this is what they look like if we're assuming that we had 4 moles of each of them. This is what the model would look like. And then we're going to mix them together. And when we mix them together, we form this lead chloride solid. And what's left in solution is the potassium nitrate. And the only reason why the potassium nitrate ions are left in solution is because there was no limiting reactant here. We're assuming that everything was used up proportionally. So the volume solution is now 200, and all of the potassium ions that we started off with from the potassium chloride, they're still in solution. So the moles of potassium ions are going to equal the moles of potassium chloride, right? Since it's a one mole of potassium to a mole of potassium chloride. And the volume of solution, though, has increased because when you mix 100 milliliters with another 100 milliliters, you're going to get 200 milliliters. And so now that's the volume. So what does my calculations look like? I'm going to take the moles to solve for the moles of K plus, I just solved for the moles of KCl. And I did that already, so I just used the same number that you have written down there, 0.30. And then I'm going to find the volume